Good afternoon, everyone. Welcome to NPTL tutorial sessions for the course Classics in Total Synthesis. So, I will start sharing my screen. I hope it's visible. So, it's our sixth tutorial session. In previous tutorial sessions, we were discussing the weekly class, like weekly lectures brief summary, and we were discussing assignment questions and some mechanisms for the reactions which are discussed in the total synthesis, and some other examples for that named reactions as well. So, we will be continuing the same pattern in today's lecture as well. So, okay, so in today's lecture, we will be discussing first week 5 assignment. There were 10 questions on week 5 assignment, and the due date was already over last week, so that we can discuss it today. And after that, we will go through the week 6 lectures, which was about the total synthesis of morphine, dendrobin, quinine, like such natural products. Okay, so we will start first with the discussion on week 5 assignment. So this is the first question. Identify the major product in the following transformation. So this particular compound is treated with lithium perchlorate and calcium carbonate in THF condition. So which will be the major product in the following transformation out of the four options given here. So I will give you a couple of minutes time to think about the answer and the mechanism of this reaction. What will be happening when we treat this compound with particularly with these two reagents. So out of the four options given here, as we can see, option A and option B indicates a ring expansion type of reaction, and option C is for epoxide formation, and option D just that tosylate elimination and an exocyclic double bond is forming, external double bond is forming. So what will be the possibility when we are treating with this lithium perchlorate and calcium carbonate? So in this reaction, as we know, lithium is involved, so it can coordinate with the oxygen present in the system. So with which oxygen it will be coordinating, that also matters because there are four oxygens in total. Two are the part of acetal and one in hydroxyl group and one in the tosylate. So here the correct answer for the question is this one, option A. So what will be happening here is like this similar kind of mechanism. First, the starting material itself is obtained by the protection of this secondary hydroxyl group selectively by using tosyl chloride, so that we will get the starting material. And on treatment with this lithium perchlorate and calcium carbonate, what is happening here is this lone pair of oxygen will fall on this bond, and this bond will be migrating towards this position, and OTS elimination will take place, so that we will get this ring expansion type of product. So what is happening here is this oxygen lone pair will fall on this bond, so that it will become double bond O, and as a result of that this bond will be migrating to here. And OTS, we are first of all we are converting that secondary hydroxyl group into OTS to make it as a better living group. So this OTS, which is a good living group, will be getting eliminated. So we will be getting 1, 2, 3, 4, 5, 6, 7. A 7-membered ring will be forming rather than the 6-membered ring. And in the presence of this hydroxyl group, we will be having this keto group there. So we will get this acetyl protected 6-membered ring fused with this 7-membered ring with the ketone group and methyl group. So this will be the major product in this transformation. Now moving to the next question. So what is the major product formed in the following transformation? This compound is being treated with SuCl2, thionyl chloride in presence of pyridine. So what will be happening? So four options are given here. As we can see in the first option, the hydroxyl group is getting replaced with chlorine. And in option B, we can see the hydroxyl group is getting replaced with an exocyclic double bond. And in option C, we can see this hydroxyl group is converting into direct a no. In option C, like one methyl group is here that is getting migrated to this hydroxyl position. And in option D, we can see hydroxyl is getting converted into chloride but in an SN2 manner. So, what will be the major product in this transformation? So, which will be the major product in this transformation? By treating the secondary hydroxyl group with not secondary, it is tertiary hydroxyl group with thionyl chloride in presence of pyridine, what will be happening? What is the role of thionyl chloride in this reaction? So here this thionyl chloride will be acting as a dehydrating agent in presence of pyridine. So what is basically happening is that pyridine being a base, as we know, it can abstract this proton from here. So it will be abstracting this proton. This pyridine act as the base and abstract this proton, and as a result, this bond will be this will be shifted to here, making it as a double bond, and this OH will be eliminating. So we will get this exocyclic double bond as a major product in this reaction. So thionyl chloride act as the dehydrating agent here. So it will take this water molecule and give this exocyclic double bond. And pyridine will also promote that reaction since it can also abstract this proton from this center, from this particular center. So here the answer will be option 2, option B. Now moving to the next question, identify the type of cycloaddition reaction taking place in the following transformation. So as we can see, this compound, this keto compound, ketone which is connected to two cyclopentenes is treated under a mercury clamp condition, and what will be the major product is already given. So we have to identify the type of cycloaddition, whether it is 3 plus 3, 3 plus 2, 2 plus 2, or 4 plus 4 cycloaddition. So here, as we can see, we are using this photochemical condition in this reaction. That is, we are taking mercuric lamp here to treat to react this compound. And as we can see, there are two double bonds here. So here the reaction will be 2 plus 2 cycloaddition reaction, and that is D-myocycloaddition reaction, which is the photochemical 2 plus 2 cycloaddition. So this compound could be represented in this manner as given here for a better understanding of this 2 plus 2 cycloaddition. So now it is more easy to visualize the bond formation. So this bonds are here, a new bond is getting formed between these two carbons, and a new bond is getting formed between these two carbon. So basically the ring will be 1, 2, 3, 4. A 4 membered ring is getting formed as we can see in this here. 1, 2, 3, 4, which is a new ring is getting formed, which is fused with this cyclopentane ring in this side, which is attached to this OCBZ group, and here in this side also it is attached to a 1, 2, 3, 4, 5 another cyclopentane ring, and this ketone also it is remaining as intact. So this will be the correct answer for this question. That is, under this Hg lamb, mercuric lamb condition, these two double bonds will undergo demyocycloaddition, that is 2 plus 2 photocycloaddition, to get this corresponding compound. So option C will be the right answer. Now moving to the next question, which is the major product formed in the reaction given below. So this ketoester is treated with this dinitrile type of compound in ethanol. So which will be the major product? Sorry for that. Which will be the major product in this reaction? So here what will be happening is that it is a type of 1,2 addition of this compound into this carbonyl carbon. So what will be happening here is a proton will be abstracted from this position, that is here, and it will attack this carbonyl center here, and this will be converted into corresponding alcohol. Then followed by that, dehydration will take place, that is alcohol will be eliminating along with one proton here, and it will be converting into double bond, and this cn will be there. So the correct answer will be this one. So this carbon, when base abstract a proton from this acidic position, it will attack at this carbonyl center, that is ketone carbonyl center, and here it will be OH, and this group will be connected to here. Then dehydration will take place, one proton will be abstracted from this, that is this will be connected to this center. Then one proton will be abstracted from this position, forming a double bond between this two carbons, and we will be getting this option A as our product. I hope it is clear. So this will be option A will be the major product in that reaction. Now moving to the next question. Identify the major product formed in the following transformation. So this compound having this alkyne, alkene and one hydroxyl group here is treated with this SnCl4 in DCM. So what will be happening and what will be the major product in this reaction? So here what will be happening is that this SnCl4 will act as a Lewis acid and it can coordinate with this oxygen. Also it can coordinate with this alkyne as well. So one Cl minus from this SnCl4, Cl minus from this SnCl4 can attack this alkyne, and thereby this alkyne will be going and attack this alkene. So this bond will be shifted to here, and this hydroxyl group which is coordinated with this SnCl4 will get eliminated. So what will be the product then? Here one Cl will be there, and here one ring will be forming. That will be like 1 2 3 4 5 6 7 membered ring will be forming with the double bond at this position, and this OH group will be eliminated. So option C will be the correct answer. So I hope it is clear. This Cl minus from SnCl4 will attack at this alkyne carbon, and this alkyne will attack this sender, forming a double bond with Cl at this position, and this alkene will migrate to here, and this hydroxyl will be eliminated to give this option C as a major product. Now moving to the next question, identify the reagents following the causing the following transformation. So here this transformation is that this double bond is getting converted into this dimethyl group. So which will be the corresponding reagents that can convert this double bond into this dimethyl group? The four options given are: first one MCPBA DCM and then methyl lithium THF. Option B, first zinc silver and then ICH2I in diethyl ether, then platinum dioxide in hydrogen condition. Then option C is the reverse of option B, and in option D we have osmium tetroxide, NaO4 and DCl, followed by methyl lithium and THF. So which will be the correct sequence of reaction and the reagents used in the following transformation? So here the correct sequence of reaction used in this transformation is option B. That is, first it is treated with zinc and silver catalyst in presence of this uh, diiodomethane, diiodomethane and diethyl ether, and then it will be treated with this platinum dioxide in presence of hydrogen to give this product. So what is happening here is, first when this exocyclic double bond is treated with this zinc in silver and this ICH2I, this double bond is getting converted into a uh, cyclopropane. Like it is similar to Simmons-Smith reaction. That is, a carbene will be formed here, and then carbene will be attacked at this double bond, and this position will also attack at this carbene. So a cyclopropane ring will be forming. Then this cyclopropane ring will be cleaved under hydrogenation condition to give this compound. So that is what is happening in this reaction. First, when we treat with this diiodoethane in zinc silver catalyst condition, it is converted into cyclopropane, followed by hydrogenation condition to convert it into dimethyl group. Now moving to the next question. Identify the major product in the following formed in the reaction given below. So as we can see, there is a diene and dienophile. So just we have to write down the Diels-Alder product in a correct stereochemical manner. That will give the result. So what will be the correct stereochemistry for this reaction? And if it is a Diels-Alder reaction, give you some time to represent it in the correct manner and to identify the correct stereochemistry of the hydrogens and the ester group. So here what will be happening is that, as we know, it is a simple Diels-Alder reaction. So this position, this carbon will attack at this center, and this bond will be shifted to here, and this bond will attack at this position. So as we can see here in this dienophile, this ester group and this hydrogen are in cis position, because the other two hydrogens will be, one will be here and one will be one group is this one. So since this ester and this hydrogen are in cis position, in product also it will be having cis stereochemistry. So there is the three possibilities, A, B and C. We can exclude this because here this ester and this proton is having trans stereochemistry. And also, as we know, this will be an endo product. So which will be the major answer? The major product will be option A, because as we know here, this proton will be to this side, that is, it will be having this opposite stereochemistry as that of this ester, being an endo product, and as well as that proton. So this correct answer will be option A. So giving this endo product with this ester and this proton at the same side and this proton in the opposite side, we will be getting option A as the major product. This is a Diels-Alder reaction under thermal condition. That is 4 plus 2 cycloaddition reaction. Due to the secondary orbital interaction, we will be getting this endo product as the major product. Moving to the next question, identify the major product in this following transformation. So what will be happening when we are treating this particular compound with allyl bromide in K2CO3, then heating it at 220 degrees Celsius followed by ozonolysis and quenching with dimethyl sulfide. So out of the four options given here, which will be the major product? So here as we can see, first when we treat with this allyl bromide, here O allylation will be taking place. So we will get this product here, allyl group will be there. Then on heating condition under 220 degrees Celsius, it will undergo A33 sigmatropic rearrangement. That is a Claisen rearrangement, and as a result, we will be getting this allyl group migrated to this position. Like this we will be getting, and here it will be OH. Then under ozonolysis condition, this will be converted into an aldehyde, and then it will be undergoing the cyclization reaction intramolecularly to form a 5-membered ring with a hydroxyl group here. So I hope it is clear. So the correct answer will be option B. That is, first step is shown here, first and second step is shown here. That is, this allylation of this alcohol under K2CO3 condition will give this compound. Then at 220 degrees Celsius, when we are heating that particular allylated compound, it will undergo Claisen rearrangement to get this rearranged product. Then what is happening under ozonolysis condition? This bond will be cleaving, and here we will get one aldehyde in presence of this alkene, and then this hydroxyl group will attack this carbonyl carbon center, and this bond will be shifted to here, and it will be OH. So we will get 1, 2, 3, 4, 1, 2, 3, 4, 5, 5-membered ring with that hydroxyl group there. So correct answer will be option B. Option B will be the correct answer. Now moving to our second last question, that is identify the major product of the following reaction. So this compound on treating with sodium bicarbonate and iodine and Ki at 0 degrees Celsius, what will be the major product in the reaction out of these four options? So here what is happening under the sodium bicarbonate ion and Ki condition, iodolactonization will be taking place with this carboxylic acid. So first iodonium ion will be forming. As you can see, there is a two possibility for the formation of iodonium ion. So one is here I plus, and another one is this alpha beta unsaturated compound I attached to here with a positive charge. So there are two possibilities as you can see, and if this hydroxyl group is opening this iodonium ion from this position, iodine will be coming at the center this carbon, and it will be 1 2 3 4 5 membered ring. On the other hand, if the iodonium ion is getting opened from this carbon, then it will be 2 one, two, three, four, four-membered ring. So as we know, five-membered ring formation will be preferred rather than four-membered ring formation. Iodonium ion and subsequent lactonization will be taking place for this particular alkene rather than this alpha beta unsaturated carbonyl compound. So it will be like this. We will get the five-membered ring instead of this four-member ring, and this iodine will be open from the opposite stereochemistry as that of this carboxylic group. So we will get this corresponding option D as a major product. So here as you can see, this alpha beta unsaturated carbonyl compound is remaining as intact, and this lactone is formed, and here iodine will be coming in the position opposite to that of the forming lactone. So this is an example for iodolactonization, where this formation of five-membered ring is preferred over the formation of four-membered ring. Now moving to our last question. Identify the major product in the below reaction. So this particular compound is heated, and what will be the resulting product out of this four options? So this is our last question of week 5 assignment. To give you some time to think about what will be happening in this reaction. So here the correct answer will be option C. And how it is forming is, as we can see, the starting material we are getting from this corresponding methyl ketone by treating it with TMS or triflite in triethylamine and DCM condition, we will be getting this OTMS. So here as we can see, there is a possibility of 3,3 sigma tropic rearrangement with this allyl system. So 1, 2, 3, 1, 2, 3. As we know in 3,3 sigma tropic rearrangement, this 1, 1 bond will be breaking and 3,3 bond will be forming. So as a result, we will be getting this corresponding product which can be redrawn into this manner. That is a 5-membered ring fused with a 6-membered ring, and all the corresponding groups are also intact. So I hope it is clear. That is, this is 3,3 sigma tropic rearrangement is happening. So we can number it as 1, and this will be 2, and this will be 3. Similarly, here we can number it as 1, 2, 3. So what is happening? This bond is breaking. It is getting shifted to here, and this bond will attack at this carbon, and this bond will be shifted to here between 1 and 2. So that will be happening in this reaction. We will be getting the corresponding product also. Option C will be the right answer for this question. So that is about the discussion on week 5 assignment. I will go through that once again. So in the first case, we saw a ring expansion kind of reaction where the 6-membered ring is getting converted into 7-membered ring when we are treating it with lithium perchlorate and calcium carbonate in THF. OTS will be eliminated and hydroxyl group will get converted into corresponding carbonyl group. And in the next reaction, we have seen this thionyl chloride and pyridine is helping in the dehydration to form the exocyclic double bond to get this as the major product. And in the next reaction, we saw a DMIO 2 plus 2 cycloaddition reaction using mercury lamp resulting in the formation of a cyclobutane ring. And in the next step, we saw how this nitrile compound is getting attacked to this uh, carbonyl carbon ketone carbon to form this corresponding, followed by dehydration to form this corresponding product, option A. Then we saw how this SnCl4 is helping this ring closure and dehydration, not dehydration, dehydroxylation to give this corresponding product, option C, as the major product. And then we saw how this like this carbene formation followed by this cyclopropane formation and the conversion of cyclopropane into this dimethyl group is carried out by using zinc, silver, and diiodomethane, and then platinum dioxide and hydrogen condition. Then we saw the Diels-Alder reaction, how it is taking place to give this compound with this corresponding stereochemistry. Then we saw how this reaction is taking place. First alylation, then 3,3 sigma tropic rearrangement, that is Claisen rearrangement, followed by ozonolysis to give the corresponding aldehyde and cyclization. Then the ninth question was about iodolactonization and how this selectivity is going, resulting in the formation of 5-membered ring rather than 4-membered ring. Then we saw this 3 3 sigma tropic rearrangement, that is scope rearrangement, to get this corresponding option C as the major product. Now we will move towards our discussion on the week 6 lectures. So, moving towards our discussion on the week 6 lectures, the first lecture of week 6, that is lecture 30, was about reserpine. And reserpine, the structure of reserpine is given here. So, to tell about a brief summary of this lecture 30, it deals with the application of Diels-Alder reaction and Bichler-Napier-Ski reaction in the total synthesis of reserpine by Woodward. So reserpine, as we can see here, is a pentacyclic compound, that is 1, 2, 3, 4, 5 pentacyclic compound, and it is isolated from the dried root of Indian snake root, which is used in the treatment of snake bites. And the first total synthesis of reserpine was reported by Woodward in 1956. And this is the one of the most complex natural product of its size. As we can see, there are out of the total 1, 2, 3, 4, 5, 6, 6 chiral centers in total, out of which this 5 are contiguous in manner. 1, 2, 3, 4, 5. 5 are contiguous in manner, and there are total 21 atoms arranged in 5 rings. And as we can see, this 6 membered ring is attached with this another 6 membered ring, and these two rings are fused in a cis ring junction. And this 6 membered ring fused with this 6 membered ring in a cis manner is constructed via Diels-Alder reaction. And another reaction which we came through while discussing the total synthesis of this reserpine by Woodward was MPV reduction. And the starting material for this total synthesis by Woodward was benzoquinone. And as I told, another major reaction was Bichler-Napier-Ski reaction. So that was the main points to be noted while we discussed the total synthesis of reserpine. Now, lecture 31 was about yohimbine, where we saw the application of Diels-Alder reaction in the total synthesis of yohimbine by Tamerlan, and intramolecular Michael addition in the total synthesis by Momos. So, two total synthesis was discussed for this natural product yohimbine. And as we can see from the structure, the core structure is same as that of reserpine, and this is isolated in 1880 from Corinanthiyohim. And the first total synthesis was reported by Van Tamerlan in 1958, which was a racemic total synthesis. uh, but in the same total synthesis, they are doing resolution to get the asymmetric compound. And this total synthesis by Tamerlan is almost similar to the Woodward's total synthesis of reserpine, and the starting material used by Tamerlan was butadiene and benzoquinone. And Tamerlan could complete this total synthesis in 1958 in 20 steps with an overall yield of 0.024 percentage from the Diels-Alder product. Now, in the Momos total synthesis, which was completed in 1990, which was the first formal asymmetric total synthesis, the key steps included were asymmetric intramolecular Michael reaction, and the starting material used was benzylamine. And he could complete this total synthesis in 13 linear steps with a 25.6 percentage of overall yield. Then the third natural product was quinine. So here in this lecture 32, we saw the discussion on the first formal total synthesis of quinine by Woodward, following Reit's protocol, and then Stokes asymmetric total synthesis. So quinine and quinidine are cinchona alkaloids, which are isolated from the bark of cinchona and remigia species, which is used in the treatment of fever. Quinine in particular is used in the treatment of malaria, and it acts as antipyretic, anti-malarial, analgesic, anti-inflammatory agent. Although quinine was not structurally complex compared to many other complex natural products isolated now, but during that time, due to the lack of techniques, it took long time to arrive at its core structure, correct structure. Also, degradation studies were carried out to assign the partial structure. And in 1853, Pasteur demonstrated that quinine is liver-irritatory, and several years later, the empirical formula was in the next year, empirical formula was formulated by Stecker in 1854, and it took several years after that also to complete the first order synthesis of quinine. And the degradation studies on quinine gave several other derivatives like quinotoxin, meroquinine, methoxyquinoline derivatives as well. Then the structure of quinine was elucidated in 1907 by Paul Rabe, and the first partial synthesis was reported by Paul Rabe itself in 1918. The first formal synthesis was reported by um, Woodward in 1944, and the first stereoselective total synthesis was reported by Stork in 2001. So, in Woodward's formal synthesis, he synthesized up to quinotoxin, which was already converted into quinine by Doring, and there he is using managed reactions as one of the key reaction. And the starting material in Woodward's total synthesis meta hydroxybenzaldehyde, and in Stokes' asymmetric total synthesis, which was completed in 13 steps, he could synthesize this quinine in 18 percentage of it. Then moving to the lecture 33, dendrobin. So here we saw the application of silver ion mediated cyclocondensation in the total synthesis of dendrobin by Livinghouse, then radical cyclization in total synthesis by Shah, and Poisson-Kant reaction in the total synthesis by Zard. So three total synthesis, one by Livinghouse, one by Shah, and one by Zard. Three total synthesis have been discussed for the natural product dendrobin. And as we can see, there are seven chiral centers in total in dendrobin, out of which six are contiguous. So as we can see, 1, 2, 3, 4, 5, 6, and 7. So seven chiral centers are there, out of which this six are contiguous in nature. So there are three five-membered rings, one of which is a lactone, that is this one, and other is a substituted pyrrolidine ring. Then there is a six-membered ring, and this compound dendrobin is isolated in 1932 from Chinese ornamental orchid Dendrobium nobile. So, in the total synthesis by Livinghouse, which was a concise total synthesis of plus or minus dendrobin in 8 steps from 2-methyl cyclopentane 2 in 1 node, the key reaction involved were silver ion mediated cyclocondensation of isonitrile with acyl chloride, and he took 10 steps to complete the total synthesis of dendrobin. Then in Shah's synthesis, the starting material was carbon, and he could complete the enantiomerically pure dendrobin total synthesis based on alpha carbonyl radical cyclization reaction in 19 steps. Then in Sart's total synthesis that was completed in 1999, he followed a chiron approach starting from verbenone, radical mediated ring opening, and Poisson-Kant reaction as the key reaction to construct the two five-membered rings, and he could complete the total synthesis in 19 steps. Then the last natural product of discussion was morphine for the lecture 34, where we saw the application of Diels-Alder reaction, Michael addition, and Woodward open or oxidation in the first total synthesis of morphine by Gates. So morphine is isolated in 1806 from opium produced by cut seed pods of poppy papaver somnifera. And there are three six-membered rings and one dihydrofuran ring with five contiguous chiral centers. And the correct structure was proposed by Robert Robinson in 1925, and the Gates confirmed it by first order synthesis in 1952, and later by X-ray the correct structure was confirmed again in 1955. Some of the other examples for natural opiates include morphine, codeine, thebaine, and oripavin. So Gates and Schudy reported the first order synthesis of morphine in 27 steps, where they used open or oxidation as one of the reaction, and the starting material was naphthalene 2,6-diol. And the key reaction in this synthesis was Diels-Alder reaction, and he could complete the total synthesis of morphine in 27 linear steps with an overall yield of 0.0010%. Then in Overman's total synthesis of morphine, which was completed in 1993, the key reaction was intramolecular Heck reaction to forge the critical quaternary center of morphine skeleton, followed by sequential iminium ion allyl saline cyclization was another key reaction. And in Overman's total synthesis, the starting material used was isovanillin, and he could complete the total synthesis of morphine in 10 steps with an overall yield of 1.01 percentage of overall yield. So that was about the discussion on week 6 lectures. I will give you some time to go through all the lectures, and you can ask any doubts if you have any. Then we will go with our discussion on the mechanism of some of the named reaction which we discussed here in this tutorial session. So I hope it's clear about all the week 6 lectures. I will go through that briefly once again. So in the total synthesis of reserpine, we have seen the application of Diels-Alder reaction and Bischler-Napierski reaction in the total synthesis of reserpine by Woodward. And then in the total synthesis of yohimbine, we have seen the application of Diels-Alder reaction, the total synthesis of yohimbine by Tamerlan, and intramolecular Michael addition in the total synthesis by Momos. Then in the total synthesis of quinine, we have seen the first formal total synthesis of quinine by Woodward following Reif's protocol as well as Stokes asymmetric total synthesis. Then for dendrobin, we have seen the application of silver ion mediated cyclocondensation in the total synthesis of dendrobin by Leavinghouse, radical cyclization and total synthesis by Shah, and Poisson-Khan reaction, the total synthesis by Zad. Then for morphine, we have seen the application of Diels-Alder reaction, Michael addition, and Woodward-Oppenauer oxidation in the first total synthesis of morphine by Gates, and we have also seen the Obermann's total synthesis of morphine, where the key reaction is intramolecular reaction and sequential iminium ion allyl silane cyclization. So now we will move on to the discussion of some named reactions which we have seen in this week 6 lectures. So the first reaction is Bischler-Napieralski cyclization. So as we can see, it is the formation of this quinazolinone kind of or quinoline kind of compound, that is treatment of this particular amide with POCl3 in toluene heating condition. We are getting this cyclized product. So we will see the mechanism of this reaction. So as we can see, the POCl3, this phosphorus is having affinity towards this particular oxygen. So here this iminium ion will be forming when this oxygen will be coordinated with this phosphorus, followed by the elimination of one chloride. Then this, to stabilize this nitrogen positive charge, this proton will get eliminated to get this compound, and then this stable compound, this POCl2, will be eliminated to give this corresponding nitrile kind of derivative. And then what is happening, because of the presence of this OMe, this oxygen lone pair will shift to this position and it will push this double bond to here, and this double bond will go and attack this carbon center, stabilizing this positive charge on nitrogen. Then again followed by deprotonation to get aromatization to form this compound. So this is known as Bischler-Napieralski cyclization, which we saw in the total synthesis of reserpine. So I will give you some time to go through this reaction, then we will move to the discussion of the next reaction. So I hope this reaction and its mechanism is clear. That is Bishler-Napierski cyclization in POCl3, how this is getting cyclized. First, this POCl3 will coordinate with this oxygen and it will get eliminated, and this OMe will push its electrons to attack this carbon to stabilize that nitrile and resulting in the formation of this particular compound. Now our next reaction is intramolecular reaction. We have already seen this reaction, that is a palladium catalyzed carbon carbon bond forming reaction, this coupling reaction between halides and alkenes. So basically, this is an example for intramolecular Heck reaction where this halides and alkene as a part of single compound. And the mechanism also we have discussed previously, that is this palladium catalyst first will undergo oxidative addition on this halide and it will form this kind of complex. Then it can coordinate with this alkene in an intramolecular fashion to form this pi allyl complex, followed by this alkene insertion to get this compound. Then beta hydride elimination will take place to give this alkene here. So it is like a carbon carbon bond formation reaction, which results in the formation of an alkene as a result of beta hydride elimination. So it requires an activated halide, that is vinyl or aromatic halides and an alkene in the same complex for the intramolecular Heck reaction to take place. Then we have opener oxidation, Merbein pond of Verley reduction, and Mannich reaction. So I'll give you some time to go through this. Already we have discussed about the intermolecular and intramolecular Heck reaction in the previous tutorials. You may go through this mechanism once again quickly. So moving to the next reaction, that is open or oxidation. So this is basically the oxidation of this particular alcohol with acetone and this triisopropyl aluminum oxide. We are getting our oxidized alcohol into ketone, and as a result byproduct of this acetone we will be getting this isopropanol as a byproduct. So this oxidation is reversible, and the reverse of this oxidation is known as mpv reduction. The reverse of this oxidation is known as mpv reduction. So the mechanism of this oxidation is like this. First, this hydroxyl alcohol will be coordinating with this aluminium, and this one of the isopropoxide will be eliminating, and this compound 3 will be forming. Then this isopropoxide ion will abstract the proton of this alcohol to form this compound 5, and this will be the resulting byproduct, that is isopropanol. Then this compound will attack with our acetone, and this acetone oxygen will attack this aluminum to form this kind of a six membered chair like transition state. Then it will undergo this type of cleavage, that is this proton will be attacking to this center, and this bond will be breaking, and this bond will be breaking to get these two compounds, which upon hydrolysis we will get our desired uh, compound 9 as the major product, and the byproduct will be this isopropanol. So this is known as open or oxidation, and the reverse of this reaction is known as mpv reduction. That is, this compound on treatment with this isopropyl alcohol, we will get the reduced compound alcohol and acetone as the byproduct. So this is Mervin, Pondorf and Worley reduction, and the mechanism is like that. First, this isopropyl aluminum triisopropoxide will coordinate with this oxygen to give this reaction, and then hydride transfer will take place to get this reduced alcohol. So these are actually reversible reaction. When we are treating this aluminum tripropoxide with this alcohol, we will be getting the ketone as the oxidized product, and when we will treat it with this particular ketone with this isopropyl alcohol, we will get this reduced alcohol and acetone as the byproduct. So this forward reaction is known as open or oxidation, and reverse reaction is known as Mervin, Pondorf and Worley reduction, which both are catalyzed by this um, aluminum triisopropoxide. So I'll give you some couple of minutes to go through this. Open or oxidation mechanism will be almost similar, because just all the steps will be reversible in nature. So mechanism of this open or oxidation and Mervin pond of Worley oxidation can be understood from the one slide itself. So I hope it is clear. And the last reaction is managed reaction, which we have already discussed in the last class also about the mechanism. So I will just briefly tell what is that reaction. That is, it is a condensation of this aldehyde or ketone in the form of enol with an iminium ion, which is produced by the secondary amine with this aldehyde, and in presence of HCl and ethanol, followed by the hydrolysis step, we will be getting this beta amino alkyl carbonyl as our compound, and this is known as managed reaction. So formaldehyde is used most often due to its higher reactivity, and it works only with primary and secondary aliphatic amines, and aromatic amines tend not to react. So that is the discussion for today's session. That is, we have discussed first assignment questions, then the discussion on the week 6 lectures, then Bishler-Napier-Elsky cyclization, intramolecular Heck reaction, open or oxidation, Mervin-Pondorf-Verley reduction, and managed reaction. So we will wait for some more minutes to see whether someone is joining or not. Then we will stop here and continue our discussion on next class. Thank you for listening. Thank you for joining. And in the next Sunday, we will meet again with the next week lectures and question discussion. So if you have any doubts or queries regarding the session, you can ask at any time. Feel free to post in the portal given in the Swayam portal of NPTL. So thank you for joining. Thank you.